The last sorting algorithm that we're going to build is insertion sort. Like selection sort, insertion sort divides the array into the sorted and unsorted part, but insertion sort puts them in the other order. It starts with the smallest value in the sorted part. One entry is sorted, and the rest of the array is the unsorted part. Notice that by sorted, we don't mean in its final position. We just mean that the things in that part of the array are in order relative to each other. In order to sort the array, we're going to take each element in the unsorted part and swap it with its left neighbor until either its left neighbor is smaller than it is, or it gets to the beginning of the array. At that point, it will be in the right place in the sorted part of the array, and the sorted part of the array will have grown by one position. Let's start with an example. In this array, we start with the 42 sorted and the rest unsorted. The job is to insert the -3 into the sorted part of the array. Since it's less than 42, we swap them. And we stop because -3 is at the beginning of the array. Now we need to insert the 16. We compare it with its left-hand neighbor 42. Since it is less than 42, we swap them. Then we compare it with its left-hand neighbor, -3. Since it's greater than -3, we stop. Now we need to insert the 52. We compare it with its left-hand neighbor, 42. Since it is greater than 42, we stop inserting, and the unsorted part has grown again. Now we have to insert the 50. Since it is less than 52, we swap them. Then we compare the 50 to the 42. Since they're in the correct order, we stop inserting. All we have left to do is insert the 5. It swaps with 52, with 50, with 42, and with 16, but then it stops because it is greater than -3. Now the sorted portion of the array is the entire array, so we're finished. Here is an animation of insertion sort. The blue bars are the sorted portion of the array. Each time something gets added to that, it gets swapped with its neighbor to the left until it's in the right position in the sorted part of the array. So that may mean that it stops because it hits a bar that is smaller than it, or it may mean that it stops because it gets all the way to the beginning of the array. Now notice this is showing swap as if you did it in place, but these swaps are going to require the temporary variable that all of the rest of the swaps have always required. Here's one to watch because it's going to stop because it gets to the front of the array, not because it runs into something that is smaller than it is. The runtime analysis of insertion sort is a little bit different than what we did for bubble sort and selection sort. For those algorithms, the runtime was the same, no matter how the data was arranged. However, as we saw in that animation, the insertion of some elements requires a lot more swaps, and some don't require any at all. So let's think about how many comparisons we have to make for the ith element. If it is less than everything to its left, we will have to compare and swap it with all of them. That'll be I comparisons and swaps. On average, if the data is random, then we'll have to move about halfway down the sorted part of the array. I divide it by 2 places. In the best case, if the element in the ith position is bigger than everything to its left, inserting it will only require one comparison and no swaps. So the best case for insertion sort would be if the array is sorted. In this case, nothing has to move. Each element of the array gets compared to its neighbor, and we realize that it doesn't have to move, so we go on to the next. That means that it will do big O of n comparisons and no swaps. If the array was reversely sorted, each thing we insert would have to move all the way to the beginning of the array. That means the first element takes 0 comparisons. It started in the sorted part. The second element takes 1 comparison, the third takes 2, and so on up to the last one that takes n minus 1 comparisons. We've shown before that this sequence is big O of n squared. So the best case and the worst case are very different. The average case for insertion sort happens when the data is in random order. In that case, every element is going to move on average halfway toward the beginning of the array. So the average runtime is half the worst case runtime. Since we drop all of the constants in lower order terms, that is still big O of n squared. So all of our algorithms are big O of n squared unless your data is already sorted.
Why would we sort data that is already sorted?
Well, we probably wouldn't. However, if your data is close to sorted, the insertion sort will be better than the others. So suppose you have an array that is sorted, and your users edit just a few values, and you don't know which ones they edited. Then the data is almost sorted, and insertion sort will be really fast.